So maybe we should get started. I hope you are a little bit interested in heat pumps, because this is what we are going to talk about the next 20 minutes. First, my name is Kim Christensen. I'm the CEO of Fenergy. And for those for whom you do not know who Fenergy is, there's a little bit of data there. I think, is it something wrong with the sound? No, it's okay. I think the most important number here is the 256 megawatts sold. And that is, when all that is installed, that is heating several cities in Denmark. So just for you to understand the magnitude of scale, that we did do quite a bit of industrial heat pumps. By the way, we are going to talk about CO2. So you can find us on 7440. That's our booth, hall 7440. It's by coincidence, but we are on 7440. Good. So what do we do? I made this very easy drawing for you, just to understand, for you to understand what we are doing. Basically, electrical heat pumps have to be powered by renewables. So, in principle, we expect that the electricity we are using in our electrical heat pumps are coming from solar, wind, hydro, whatever is renewable. Otherwise, it doesn't really make sense, because we want to basically decarbonize the heating sector, and we want to electrify the heating sector. But of course, we are not decarbonizing anything if the electricity is coming from, burning fossil fuels, basically. So, power from here into the heat pump. We heat the water that we need to heat on the user side. But of course, a heat pump needs an energy source, a heat source. And we basically don't care where it's coming from. It could be waste heat, which is a good idea if there is any waste heat, but it could also be a natural source. And a natural source is what we have available in nature. It could be groundwater, it could be air, it could be the sea, whatever is available. The issue is that we heat water. But the issue is also that the energy source we use to drive the heat pump, which is the electricity, is not available all time. So we have to be able to run the heat pump while the electricity is cheap. But it doesn't necessarily mean that the heat is used in the city. So we have the opportunity to store the heat in a hot water storage. So we produce all the heat while the electricity is cheap or available, and we use the heat when the city needs the heat. And in this case, you have to imagine that district heating, in our eyes, doesn't have to be heating a city. It could be a university campus, it could be a hospital area, it could be industrial area, doesn't need to be an entire city. So this is the concept. And of course, the heat pump is what we are trying to do and manufacture. We do not only sell the heat pump, we are also selling basically the entire project. So we are also helping in the installation, we do commissioning, and we do service. So a project could look like this. It's probably a pretty average project. In this case, it's a 4 megawatt heat pump. It's CO2 as refrigerant. And here you see the outdoor energy collectors. So that is the heat exchangers taking the heat from ambient air. A lot of the heat is actually condensation of the humid air. So there's a lot of water dripping from the collectors because we're cooling air below the dew point. So all the heat goes into the heat pumps, and the heat pumps are placed inside the building, and they will probably look a little bit like this. Basic rack with compressors. Then of course we also have a defrosting module, and of course we have some controls. So that is what a project consists of. The rack itself, horizontal receiver, a number of compressors, ejector technology, most probably because heat pumps is very, very happy with ejectors because we can use them all the time because the high pressure is already there, driving the refrigerant through the ejector, recovering energy from the system. Well, that's basically it. And if you want to do big heat pumps, this heat pump may be 2 megawatt. If you want to do 10 megawatt, we multiply. It could be 5 of these units. Then we do 10 megawatt. Not that difficult, actually. So schematics around our main design is a configuration with evaporators. Now we talk about air source heat pumps. So this is the energy collector, the evaporator, taking the heat from the ambient air. Empty compressor compressing all the way up to the gas cooler, rejecting the heat into the district heating system, back into the receiver through a high pressure valve. But of course we have ejectors, so most of the motive flow here is going through the ejector. The ejector is lifting free of charge gas into the receiver, and then the IT compressors or the parallel compressors are compressing vapor from the receiver up to the same pressure level as the empty compressors down here. So that is the basic CO2 cycle. You will find the same kind of cycle in a supermarket, just a much smaller system, of course. In this case, we have to defrost as well. When ambient gets below 5 degrees, we have to defrost. And how do we defrost? The idea is that we take heat from the return water from the district heating grid. The return water could be 50 degrees, it could be 45, it could be 35, but we have plenty of heat available in that return water, and we are heating a glycol loop, and we are then heating the circuiting in the evaporator. Of course, we have to pump it down first. We have to stop the fans before we start to use the glycol, hot glycol, into separate passes of the heat exchanger. So that is the way we do the defrosting. So the heat pump is still producing heat because we're not defrosting all the sections of the evaporator. We're just taking one section, all the other sections of the evaporators are still running. While when that is defrosted, we continue defrosting the next one. So the heat pump is not stopped. It produces heat, but at a little bit reduced level. That is a demand in a real heat pump that you cannot, it's not like a household heat pumps or residential heat pump where it's stopped and it takes the heat from the house. This is not the way we can do it in district heating. I hope you get my point. It's pretty simple piece of equipment, actually. So, a little bit about the market. Selling heat pumps into district heating, it requires that we have district heating systems, or district pipes in the ground, basically. And these columns shows, the red column shows what we have today. The green dot shows what we expect that Europe would have in the future. And there's a bit of a difference there. So we need to dig a lot of pipes into the ground. But basically, just to give you a number up here, we predict to get to the level of electrical heat pumps in district heating in Europe, we have to install, not only us, we need a lot of help from you guys, also installing heat pumps, probably 2,000 megawatt per year, every year from now on until 2040. So there's a lot of heat pump capacity we need in the heating system to decarbonize. If we go into the industrial sector, the market potential may be even higher. Because if you look at the total pie here, a lot of the energy used in the industry is actually for heating. Unfortunately, only a little bit is used for processes below 100 degrees. It's actually 25% of the heat. But that's just that part is alone as much as we expect to install in district heating. Then we have the more difficult applications. That is high temperature heat pumps below 200 degrees, from 100 to 200 degrees, and the really high temperature heat pumps, which is probably not available right now, but somebody are working on it, above 200 degrees. There's a huge potential there. That is if we want to decarbonize the whole industry. So the potential is really, really big here for heat pumps. So just running through some of the case stories, I think you have to grab only a few points in my presentation today. First one is, I would say, grid balancing, and I mean electrical grid balancing. We cannot use electricity which is not there. We need to use electricity while it's available. So being able to stop heat pumps is extremely important, and to do it very fast is important to frequency regulate the electrical grid. How can we do it? We need to have big hot water vessels, and that's why you see this on all our installation. You have these very big hot water. It's actually kind of electrical storage, you can say, because we run the electrical heat pump while electricity is there, filling up the storage. So that is one point. The other point is temperatures in the district heating grid. For heat pumps, we need lower temperatures than what we have historically had in Europe. In Denmark, we are a little bit lucky because we have what we call fourth generation of district heating, low temperature district heating, but in many, many countries, the temperatures are too high. Especially for CO2 heat pumps, we need the return to be lower. So that's the second topic of today, lower return temperatures. So typically, vessel sizes are around a 12-hour vessel size, so we can stop the heat pump on the coldest day 12 hours. So that's a size. Now it is summer 12 hours, and the winter it should be minimum 40 hours. 12 days and 40 hours, sorry. I just run through some pictures of what we are doing. This is 4 megawatt. Sometimes we put panels around, maybe for noise reasons, maybe for cold air recirculation reasons, maybe for visual reasons. So there's an opportunity to do that. We also have to acknowledge that doing the green transition have some penalties to the neighbors. Think about this installation. This is your house, but this is the hot water vessel. In the morning, you look out at a very big vessel now, but it's needed. They probably asked that neighbor, is it okay to build that vessel? And he said yes, because the district heating price was going down. But a lot of the district heating companies are in the middle of cities. The city grew around the district heating company, and now we're installing heat pumps. And the energy collectors are here. The heat pump is actually inside that box, because you didn't have space for it inside the building. Yes, this is a 7 megawatt heat pump. And again, a lot of vessel capacity here, and the heat pump's inside a nice building there. Another picture here. You just get a little bit of, there should be a video here, but maybe not. I will see. No, that's okay. This is a combined air source heat pump and wastewater heat pump. So you have the energy collectors here. Here you have the ponds for wastewater, but the wastewater is warm, so why not cooling down before we release it into the river? So we're cooling the cleaned wastewater before it goes into the river. So that's just, of course, another nice thing with wastewater. We can use that for the energy source or heat source. And so far, this is our biggest heat pump, is 11 megawatt. We are doing another 16 megawatt very soon. So they can be rather big, the air source heat pumps. Sometimes space is limiting because we're in a city. You would normally think that is the gas cooler, the condenser on that roof, but it is actually the evaporator. It's the energy collector collecting heat from the air for the district heating network surrounding these buildings. It's in London area, this one. Yeah. We also do smaller heat pumps, but I'll jump a little bit because of time. This is actually a nice system because here we are helping IKEA. We are refrigerating IKEA during summertime. All the heat we are taking out of IKEA is dumped into the district heating network. If they do not have space for the heat because they're not using it during summertime, we can reject it in the gas coolers here. But these gas coolers can be reversed. So during wintertime, they are evaporators. We are taking heat out of the air, and the heat pump is putting heat back into the IKEA. So it's a kind of a reversible system. but also combined, we can do both things, heating and cooling at the same time. The last project I think we will show is just this iconic building in Copenhagen. It's a district cooling, district heating combined solution. So all the heat we take out of the district cooling network, we are rejecting back into the district heating network. So that's really a good philosophy, I would say. So challenges, what we see. Of course, when we do air source heat pumps, the penalties we could have is, of course, one side is defrosting. During wintertime, we have to defrost. But another penalty that could appear is that we have what we call cold air recirculation, meaning that the air that we just cooled down is recirculating back into the same evaporator, and we try to cool it again. And in that way, in the end of the day, we could create a lot of cold air around the energy collectors, and the COP and the capacity will be very poor. So what we do is internally that we have the capacity to do CFD calculations in different wind direction and wind speeds. And of course, we have the wind rows somewhere. So for that specific location, we know what are the predominant wind direction and wind speed. And we can simulate what would the effect be on this installation. It's more or less necessary to do this. Otherwise, you can end up in a situation where the heat pump is not a really good piece of equipment. Of course, defrosting is another thing. I explained the sequential defrosting. We also have what we call the winter functions. We have, of course, during snowfall and the heat pump is stopped, we would like to run the fans anyway at slow speed because we blow the wind upwards and then the snow is not falling on the fans. Because if snow falls on the fans and you want to start a heat pump, you cannot start it because you can't get any airfree. We also have what we call the city weather button. City weather is for a heat pump is very humid conditions, just around 1 or 2 degrees. And we cool the air down and we get sub-zero temperature and all the water in the air freezes to ice. And the ice will settle on the fan or the diffuser. We need to avoid that. What we can do here is simply to increase the fan speed. And it's really effective way just to avoid shitty weather problems, I would say. I would just show a video. We are defrosting now. The others are still running. The neighboring are still running. So a lot of water comes out, we defrost for 15 minutes, go to the next one. While we are defrosting, it's important to keep the hot air inside the coil. How do we do that? Fans are stopped, but we can actually start and stop the fans. If we see that cold air is dropping down, or hot air is dropping down, or flowing up, we can reverse the fan so we keep the whole hot air inside. It's very important to remember to keep the hot air inside melting ice instead of just heating air to have high efficiency during defrost. Small tricks for you when you want to compete against us or buy a heat pump from us. That's maybe more easy. Fluctuating prices on electrical grid, we touched it already. It will be everyday life because what are the weak point when we electrify? It will be our electrical grid. And we have to protect it. So the good news is we get money for protecting the electrical grid. So we have to start working on the grid balancing issues here. So in Europe, I can see that maybe some of you outside Europe, but electrical grid balancing is something that we work with in Europe. And if you have either your producer of electricity or consumer of electricity, you get paid to help the electrical grid every second. So to be on the very fast track here, normally heat pumps are working here, in this area 15 minutes. We need to make the heat pump much faster so we can frequently regulate the electrical grid with very fast stop-starting of compressors. So that's what we are aiming at, getting down to, FCR is 30 seconds, and that's what we are aiming at with our heat pumps. Stopping compressors. Can you imagine? So every time we see that the frequency drops to, let's say, 49.8 hertz, we are stopping compressors. If it raises to 50.2, we have a 50 hertz network in our country. If it raises to 50.5, we are starting compressors. It's extremely important. Much more important than CUP values. Much more. So we should be just as fast as an electrical boiler, more or less. I don't want to jump into it. It's one of the points you should remember from my presentation is district heating network temperatures, cold return, cold return, cold return. And the reason is that when we need to heat water with CO2 as refrigerant, we are cooling the green curve with CO2, and the lower you get in this corner, the better COP you have. So entering the heat pump with a low temperature, it's very important. What do we do if we don't have cold return? We can add mechanical subcooling. So I will just explain briefly. We add an additional heat pump here. It could be our isobutane heat pump. This is 50 degrees return, which is probably reasonable level in Europe. It's very high in Denmark, reasonable level in Europe. But we add a isobutane heat pump here. We cool down the return, and we heat some of the water to 80 degrees. Now the CO2 heat pump have 40 degrees instead of 50, which is really nice temperatures for the CO2 heat pump. And then now we are heating water to 80 with the CO2 heat pump. So basically the isobutane as a mechanical subcooler is helping the CO2 heat pump to get back in the game on COP and efficiency.
We only have 30 seconds left.
Yeah, I knew. Good. Just this slide. There are so many things that you have to be aware of. Will heat pumps come to us to talk about it? It's not only the COP, that's my point on this one. And this is our product portfolio. We mainly do CO2 heat pump, but also propane and isobutane. And I think basically that was my last slide. So thank you very much.